All right, so today we are going to continue our series on what modern processor has done in making your program more efficient so that you won't feel like whenever I'm running my program, I'm at DMV. But before we start, let's see what efforts has we been reviewed. So first of all, we said ideally we want pipeline processors to help us achieving shorter cycle time but also the sense throughput as a native implementation of one instruction per cycle. However, we figure out that's almost impossible because we have 3 different types of hazard. Structural hazard means that the hardware components doesn't allow me or doesn't allow the processor to schedule 2 instructions on the processor at the same time to make both making progress. And the second type of hazard is control hazard, means that, well, to achieve throughput that is equal to a single cycle implementation, a single pipeline should be able to continuously fetch new instructions. However, because I have branch instructions or some other instruction that make me uncertain about who is the next instruction to execute, so I'm not able to continuously fetch an instruction. So that's control hazard. So for control hazard, we have been talking about star can help the address the issue, but it simply solve the issue doesn't make your performance better. And to improve, to make the performance better, we'd actually have static. We actually saying that branch prediction is probably the solution. And in terms of branch prediction, we talk about 4 different types of dynamic prediction mechanisms: the local bimodal, the global 2-level, and also perceptron. Teach there's 2 types of hybrid predictor. We also talk about tournament predictor. So we actually talk about 5 different branch predictors. And now we are at a stage that we talk about data hazard, and we have been talking about, instead of stall, we can also do data forwarding. However, even with data forwarding, we are still not satisfied, because data forwarding, although data forwarding allow us to continue resume instruction execution whenever your data is already available in the pipeline before it reaches the register file. However, if you examine the performance, for cases like this program, like this swapping program that we swapping 2 arrays, we still have to wait for 3 cycles every time because of even though we have the data forwarding, right? So that's actually not ideal, right? So however, in the last lecture, we demonstrate if you are allowed to reschedule instruction across the branch, you actually have a lot more opportunities that you can exploit. So that's why we have been talking about mechanism, how to perform dynamic instruction scheduling. And the mechanism is actually documented in a paper that we introduced you. That's actually, and it's actually a very widely adopted approach in all modern processors. So this mechanism is called register renaming and speculative execution. And so register renaming, it comes from the fact that if we are allowed to give each instruction a new output, each instruction instance a new output, we should be able to get rid of all the false dependency and allow us to freely schedule our instruction only looking at their data dependency and the availability of your LUs. So, so register renaming is a hardware implementation of that. And if you are familiar with the compiler and if you are familiar with the LLVM, you will figure out that LLVM IR actually does very similar things as register renaming, but in a software way for their instruction scheduling. But let's set that aside. So for register renaming, its idea is that, well, since if we want to get rid of false dependency, all we need to do is that for each instruction that generates an output, I give it a new register or temporary storage for that output. So that places that where we store those temporary outputs are called physical registers. So whenever an instruction enters the pipeline, the register renaming stage, the mission of the register renaming stage is that I find a physical register to store that temporary output. And for all the following instructions, depending on that renamed instructions, as long as one of its input is depending on the output of that instruction, the input should be renamed as the physical register of that instruction. So in this way, you are kind of like decouple all the data dependency occurs because of the limited number of registers, architectural register you have. So conceptually, right now, you can imagine even at the register level, the computer is trying to virtualize register in a way that the registers that instructions or programmers see are so-called architectural register. You can consider it's like virtual memory, so it's virtual register. And the physical registers are where you actually have your data and instruction accesses. One thing that is a little bit interesting, fun fact, right? So in virtual memory, we are allowing programmer to use more memory than your physical memory. However, here we are actually doing a flip, right? Your physical register are typically more than your architectural register, because the reason why we want physical register is because we want to provide temporary storage for instruction execution. And those instructions might all share the same register names. So we are actually making one register name potentially associate with multiple physical registers. So that's why we need more physical registers than architectural register. And finally, when we figure out that, okay, the physical register value that I'm waiting is ready, whenever I feel I found out that all the LUs that I want to use is ready, and in the meantime, those ones who are available, there's no one in front of me. Why not having me go ahead, right? So that's the scheduling policy. So, however, it sounds like we can execute instruction out of order. However, there are restrictions here. So first of all, the dynamic instruction scheduling is based on the fact that we are able to continuously fetch instructions because of branch prediction. So whenever you are making a prediction, there's always a case that you might get it wrong. So we don't want to get our execution result wrong. So you need to have some mechanism to retroactively reclaim or say recover from the mistake that the branch prediction made. And also, one more thing, even though there's no branch prediction involved, during the normal instruction execution, there are always exceptions. So for example, if I have a data memory access instruction or any instruction that needs to access memory, it's pretty natural that once in a while you will meet an event called page fault because the page is not mapped to the physical memory yet. So at that moment, it triggers that exception, and then it requires the operating system to handle that fault. So the mechanism is actually that the instruction will raise an exception, and that exception would caught the processor's attention, and the processor needs to modify the program counter to where the operating system handler that handles the page fault to continue execution. And after you are done, going back. So in this way, you can consider an exception is potentially like an unexpected branch in your code that I will jump the execution to another pieces of code that I'm not supposed to, right? And exceptions, page fault is only one of the exceptions. So if you have floating point errors, if you have memory out of bound error, if you have segmentation fault, if you have divided by 0, they all need the operating system to take care of. And it means that how often do we need that? And how much is the chance that, so every instruction would have the chance of meeting an exception. So what does that tell you is that although in theory, we can schedule instruction out of order, execute them out of order. However, because exceptions occurs every time, all the time, because branch prediction may be wrong anytime. So you cannot actually make those results available to the user program unless you are 100% certain that this instruction is going to be done. All the priori instructions are executed without an exception. So turns out you need a mechanism that to make sure that instructions that are not 100% certain to be executed should not present its result to the rest of the world. Or if I figure out there's anything wrong in a priori execution, I am allowed to recover those errors. So by default, when the instructions start executing in an out of order fashion, every instruction is considered as speculative. What does that mean by speculative? It means that I am guessing this instruction may be executed. So because you schedule instruction in a speculative way, so whenever the instruction enters the pipeline after it's being renamed, you need to store the information regarding this instruction in a spatial unit called reorder buffer. So the reorder buffer is typically combined with an instruction queue. So it's a first come, first served circular queue. So it must be kept in order, otherwise it shouldn't be called reorder buffer. And the reorder buffer, whenever an instruction enters, it will keep track of what kind of opcode of this instruction is, where the source operand, which is where are the source operands, which is pretty much the renamed physical registers, and also who is the target operand of this guy. And then after that, right? Once the instruction start executing, the instruction could be executed normally, and then finally, at the end, the instruction after its execution, it will make its change to physical registers, but it's still going to be a speculative state. And only when, and the instruction will stay in this reorder buffer until all the instructions prior to this instruction has been considered as completed without any issue. And only when that point, the instruction would be considered as non-speculative and ready to be commit. And by commit, it means that we finally made a result available to the rest of the world, and the processor can tell the software, I'm done with this instruction. So that's the internal logic of speculative execution. Here is what you need. So this is the current pipeline we have. It supports data forwarding. But if you want to support register renaming out of order, then you have to add register renaming logic, which renames each output and rewrite all the source operands. And also put it, after you rename the instructions, the instruction will be stored in a reorder buffer combined with the instruction queue. And then there is always going to be an entry in the instruction queue for each instruction until the instruction is considered as non-speculative. So that's the whole life of an instruction in this modern processor. And this is still true for every processor that you are using right now. So with that, here is the execution flow of these two loop iterations that we previously have been seeing. So remember, with the best compiler optimization, we are only allowed to shrink one stall. So we are still at the fact that we have to run 7 instructions in 9 cycles. But how about register renaming? So first of all, in the first register renaming, you have to add one pipeline stage called rename stage. At rename stage, it means that I already put this instruction in the reorder buffer, and I also find a physical register that can store the output of this instruction. And all my inputs are rewritten as the source register using physical registers. So that's the renaming stage. And so the first 3 cycles, we don't have any issues because there is no one blocking the execution of instruction 1. So now, at the 4th cycle, because instruction 1 is using memory unit to perform its execution, and there's no one blocking in the memory unit, and I have all my execution, all the values that I need that is ready. So I can pretty much put instruction 1 inside the memory stage as the execution. And at this point, in my physical register and architectural register table, it will say RSI is in P1. So in the future, if anyone is referencing RSI, it will check P1. And then, but if you look at P1, it's currently invalid, but in use, meaning that someone is generating its result. So if there's any instruction that needs P1, at this point, you cannot proceed. So now, in the next cycle, we renamed instruction 2, and instruction 2, in sequentially, we will put it in P2. And so in the next cycle, instruction 2 can go into the memory stage because the first instruction already moved on from the first memory stage to the second memory stage. So now, looking at instruction 3, this instruction doesn't have any new output. Instead, it relies on the input of P2. So if you look at the current register table, is P2 going to be ready in the next cycle? The answer is no, right? So which means that there's no way we can execute instruction 3 in the next cycle. So there is still going to be so this cycle, right? We are not issuing any new instruction. By issue, it means that the processor put an instruction into the first stage of an execution. So And for this processor we have right now, the issue logic only has the ability to pick one instruction into one functional unit at the same time. So right now, none of the functional units has a new instruction coming in. So this cycle, we do not issue anything. So in the next cycle, we already have register 4 renamed. However, instruction 4. However, instruction 4 is depending on RSI, which is currently in P1. But in the next cycle, P1 is not ready yet, so we are not able to continue instruction 4. So you can imagine in the next cycle, we are not going to put any instruction into execution. So that's why in the next cycle, we are not doing anything. However, in the meantime, we can continue in queue a new instruction called instruction 5, which generates an output to P3. However, if you examine what instruction 5 is relying on, it's not depending on P1 or P2. So we can pretty much put instruction 5 into execution in the next cycle. However, here, okay, I think here, you figure out that I select instruction 4 in the next cycle for execution. Because, again, be careful about this. As I said, this issue logic only allows one instruction to be picked into execution. So in this way, both 4 and 5 are available at this time. However, because 4 comes before 5, so according to the rule, I have to let 4 go first, right? So that's why here we only have 4, but not 5. But keep in mind, 5 is actually ready, right? However, one thing that's also interesting to see, even though I put 4 ahead of here, it's already before the execution of 3, right? So you already see with register renaming, with this kind of execution philosophy, I'm actually able to reorder instruction 3 and 4 regardless what's their compiler order. Now, at the next cycle, you will know P2 will be ready as well. So then the next instruction we can pick for execution is actually instruction 3, right? So in the next cycle, we will put instruction 3 for execution. And in the meantime, the instruction 1 was originally at the reorder buffer. However, after checking all prior instructions to instruction 1, there's no one before instruction 1 still being non-speculative. Then instruction 1 can become non-speculative, means that we can commit the result of instruction 1 to the rest of the world. So that's why I cross out instruction 1 here, meaning that instruction 1 has done everything it needs to be done, and it has to be retired from this reorder buffer. And but in the meantime, let's check this, right? So instruction 3 is put into execution because it's the very first, the oldest instruction that hasn't been issued, but it's available. And in the meantime, because this is a one issue processor, meaning that only one instruction could be executed. So that's why here, even though 5 is also available, but I'm only allowed to execute 3. And in the next cycle, finally, we put 5 into execution because now 5 is the oldest one that hasn't been issued, but available. So, and also for instruction 2, because 1 has been committed, so after check that out, 2 is the oldest non-speculative instruction, so in a reorder buffer, so it could be committed as well, right? So the next cycle, right? Now we will consider. You can imagine 4 and 3, they are continuously making progress, and 5 will make its result available. So if you look at the instructions that we have in the queue, right? 6 can execute, agree? And also 8 will be ready for execution because for instruction 8, it only depends on RAX. And once you finish instruction 5, both instructions will be available. So at the next cycle, we can imagine the right instruction to put into execution will be 6. And in the meantime, 4 and 3, they will continue execution. Now, I renamed one more instruction code 9, and 9 is depending on RX, and this is already being resolved by 5. So you know whenever it comes to instruction 9, or whenever all instruction before instruction 9 has been issued, instruction 9 should be ready to be issued, right? So now in the next cycle, I have instruction 7, 8, 9, right? Who can I put into execution? Or who should I pick for execution? 7, right? Because it's the oldest. It's depending on the result from 6, and 6 is done, right? So 7 is put into execution. And now, how about the next cycle? Who am I going to put in there? 8, right? So A should be put there. So here we should have an 8. A should be put in there, right? And we still have, I think I'm a little bit off on this. So 9, 10, 11 should be in the queue still, right? And as I said, next cycle you are ready to put 9, right? And then the following cycle, right? The following cycle, right? We should have 10, 11, 12, 13. I think the table is run in some way. Wait. Okay. Okay, so if you continue running this table, right, you will figure out that, yeah, I think I made it wrong. So so roll back to this place, right? If I'm at cycle 15, 10 is, at this moment, 12 should be ready to execute, because 12 is actually only depending on 5, right? And 5 has been done way a long time ago. So 12 could be put into execution, and 13 is depending on 12. So 12 and 13, they can be executed consecutively, right? So then finally 11, right? So if you continuously looking at this figure and continuously complete this pipeline diagram, one thing you will find is that after this point, right? Did you see that? After this point, every cycle, I'm pretty much issue a new instruction, right? So here I issued A, here I issued 9, here I issued 12, here I issued 13, I issued 11, I issued 10, and then continuously I issue 14, right? So every cycle I am issuing a new instruction. What does that mean? What does that imply? The CPI is actually equal to 1, right? 7 instructions in 7 cycles, right? So CPI is equal to 1, right? Isn't that the ideal CPI of a pipeline processor? No? Why not? If you have a single pipeline, what's the maximum you can get? 1, or minimum you can get, right? It's actually 1, right? That's perfect, right? With register renaming and overloader, we finally fully utilize the pipeline. Okay, so some of you might be asking, okay, during the exam, I don't have that much time to complete this table, right? Is there an easier way to make this analysis? So throughout this class, this is what I expect you to do. So first of all, right, imagine, what's the rationale behind register renaming auto order execution? We want to schedule instruction based on what? What? Hardware availability, that's 1. What else? Even though I have available hardware, what should I be executing? What kind of instruction is ready to be executed? What? Decoded instruction, what else? Can every decoded instruction be executed? No dependency. Or say all the dependency has been resolved. What does that mean? What does that imply? I have to schedule instruction based on what? Data dependency. So what kind of representation can tell you the data dependency among instructions? What kind of representations? I mean, I have been talking about this for lectures. No, not that's the mechanism, right? What kind of representation? Directly a cyclic graph, right? So it's data dependency graph, right? Okay, that's a very compiler discrete math usage, but data dependency graph, right? So what you actually need to do is that draw the data dependency graph and then you will figure out. If you don't trust me, let's walk through it. So first of all, in the first cycle, I would decode the very first instruction, right? So at this point, because I just decoded, so I wouldn't imagine anything to occur. In here, on my data dependency graph, I kind of like separate them into 3 columns, which means 3 different functional units that I can issue an instruction at any cycle. So what does that mean? If I put an instruction into that functional unit, means that at that time, I'm issue an instruction using that functional unit. So the first instruction, what kind of functional units am I asking for? Which one? Memory, right? So in the next cycle, am I ready to put instruction 1 into execution? Right? So in the next cycle, I can issue instruction 1. And in the meantime, I would have 2 in my queue. So which functional units is 2 targeting? Memory. Is anyone targeting at memory at the next cycle? Targeting issue at memory at the next cycle? No, right? So 2 could be issued in a memory unit in the next cycle. How about 3? Who is 3 depending on? 2. How many cycles it takes for 2 to finish the memory? 4, right? By default, in this class, if I didn't mention elsewhere, it's 4, right? So, okay, 4 cycle later, right? So it means it can only start at this point, 4 cycles later. Agree? Right? So now for instruction 4, who is it depending on? 1, right? Okay, so where is the earliest place I can have 4 executed being issued? What? Right before 3, right? Okay, how about 5? Okay, so 5 have to issue anyway after this, right? But because we have only 1 issue pipeline, right? So this 2 has occupied the following issue slots, right? So when is the earliest time I can start executing 5? What? After 3, at which functional unit? LU, right? So that's 5. How about 6? Is after 5? Okay, right? So 6 is after 5. How about 7? After 6, right? It's, well, after 5, to be honest, right? After 5, but because 6 already occupied that pipeline, right? Occupying that issue slot, so I can only have it starting after 6. How about 8 for the 8th instruction? When is the earliest point that I can execute it? After 1? Who is 8 depending on? 5. So it's depending on 5 because of Rx, right? Theoretically, this is the earliest place I can start. But remember, this is a 1 issue pipeline, right? So I can only have it starting here, right? So 8 can only start here. How about 9? Who is it depending on? 5. But again, because 8 occupy that issue slot, so it can only start here. How about 10? After 9? No. Who is 10 depending on? Who 10 depends on? 9. So how many cycles take for 9 to make its result available to 10? 4 cycles later. So 10 has to be earliest here, right? Similarly, for 11, it's earliest here, right? So how about 12? Who is 12 depending on? Who is 12 depending on? Who is 12 depending on? 5, right? Okay, so it's depending on 5. So when is the earliest issue slot I can allocate for 12? After 10? Why after 10? After 9, right? Because I have no business with 10. And there are still 2 slots that are empty here, right? So 12. How about 13? After 12, right? How about 14? After 10, right? So 14 will be here, right? So that's pretty much the same issue flow as the pipeline method, right? And again, if you check the graph carefully, you'll figure out after this point, every cycle, I'm issuing a new instruction. So my CPI is also 1 based on this data flow analysis. Okay, so far you might think, okay, am I limited by CPI equal to 1 in any processor? Question? Uh-huh. After 2, because at this time you haven't even renamed it. You haven't even fetched it. Yeah, it's not in it, so you don't have it yet, right? Okay, so now you might think, is CPI equal to 1 the limitation? Can we surpass that in limitation? So here comes the idea called superscalar. Superscalar. So what does that mean by superscalar? So here's the thing. If you think about your processor, in addition to 1 functional unit, we actually have many functional units. But there are a variety of reasons that we cannot activate those functional units together. First of all, like you said, right? Why can we like execute 5 earlier? Because 5 is not even in the queue yet, right? So what does that mean? I need to fetch more each time, decode more each time. So I have more instructions that is available for me to choose, right? So one of the basic thing for a superscalar processor is that you have to increase your fetch width, which means that your processor needs to have the ability of fetching more than 1 instruction. And typically, the fetch width means how many instructions that I can fetch and decode each cycle. And a second parameter that affects the superscalar performance is that, okay, even though I have many instructions in my queue, but if I don't have the ability of making multiple instructions using different functional units simultaneously at the same cycle, then I'm not allowed to make my performance better. So the ability of making your processor putting more instructions into execution is called issue. So issue with means that I'm available, the availability of your hardware in executing the instructions. So for example, if issue width is equal to 2, means that my processor concurrently can put 2 instructions into execution. So theoretically, with this kind of processor design, your theoretical CPI would be the minimum of your issue with fetch width and decode width. One over this, right? That would be your minimum CPI, right? So if all of these are 2, right, you can actually achieve CPI equal to 0.5, right? So let's see how does that work. So here's the thing. This is the original pipeline we have. And our idea is that we want them to work together at the same time. So first of all, you want to make sure that my issue logic is available to put multiple of them into execution at the same time. But also, I want to have more instructions in my pool to choose. So it turns out this is what you have to do, right? This is what you have to do. So what you have to do is you have to have multiple instructions in execution. you have to fetch multiple instructions, and the instruction you also so here I put 2 arrows, means that I'm fetching multiple instructions at the same time, right? And also you must be able to decode multiple instructions, rename multiple instructions, put multiple instructions in a reorder buffer, and issue multiple instructions, right? So that's the idea of superscalar, just widening the bandwidth in decoding and fetching and renaming and issuing instructions. However, what you don't necessarily need is to have more functional units than what you have for now. So you might be curious, okay, so given the same amount of functional units that I have currently, can I really make my CPI like 0.5? So let's take a look of the same pieces of a code. And now the only thing that need to change is that you are able to pick 2 instructions that are ready in a queue at the same time. And every time you can see at the end of instruction cycle 3, I already have 1 and 2 in execution. So at the next cycle, who can I put into execution? Why only 1? Because 1 and 2, they both want to use memory unit, but again, we did not double the number of ALUs or functional units we have. So still only 1 memory instruction can go, right? So 2, 4, 3, and 4, they are all in a queue still. Okay, let's consider the next cycle. 2, 3, and 4. Is there anyone that I can put into execution? 2, right? But again, because 3 and 4, they are all memory instructions, so there's no way I can put them into execution. But in the meantime, I keep decoding, so I have 5 and 6 coming in. So 3, 4, 5, 6. Who can I execute in the next cycle? 5, right? Because 5 is not depending on anyone else. And in the next cycle, there's no way I can execute 3 and 4 because of data dependency, right? And for 6, it's depending on 5, so they cannot actually be run together. So the next cycle, only 5 can be put into execution. But at this moment, at least this cycle, I'm executing something, right? But previously, I'm waiting, right? So now, how about the next cycle? I have 7 and 8 in addition to 3, 4, 6. Who can I put into execution? 6. Who else? Only 6. Only 6? 7? Why can I execute 7? 7 is depending on 6, right? So 7 cannot, right? Anything else? Anything else? Eight. Why 8? 8 depending on 5. 5 has already completed. What else?
And 8 is moved. It's a memory.
And no one is going to use memory and no one is going to use M1 in the next cycle, right? So 8 and 6. All right. See, we are more aggressive now, right? So how about the next cycle? Who can I put into execution? 3, right? Because 1 has been done, right? How about 9 and 10? Are we able to execute them? Probably not, right? Because if you want to put 3 into execution, right? So, why am I? Oh, sorry, not 3. Oh, it's actually 4, right? 4 can be executed, right? Right, because, right, 4, not 3, right? Because 4 is depending on RSI and 1 is done, right? So actually 4. And also 7, right? Because 6 is done and no one is using BR. right? And I can issue 2 instructions. So 7 could be executed, right? And 1 is done, so we put it in the reloaded buffer, right? And in the next cycle, 1 could be retired because no one in front of 1 is still non-speculative, right? So if you keep drawing, right, you will figure out something interesting, right? See, my performance is pretty good, right? It seems like every cycle, I almost can execute 2 instructions almost every cycle, right? But again, I don't like that because it's too complicated, and data flow graph is what I like the most, right? So first cycle, I have 1 and 2. So who am I ready to execute in the next cycle? 1, right? So next cycle only 1. And in the meantime, and I know 2 will be after that, right? That's the earliest time 2 can be executed. How about 3 and 4? When can they be executed? Again, right? This part is similar because the only thing that you cannot reorder is they have data dependency, right? So you have to wait for 4 cycles still. But in the next cycle, I got 5 and 6. When is the earliest time I can execute 5 now? After 2, right? And when is the earliest time I can execute 6? Right after 5, right? And I got 7 and 8. When is the earliest time I can execute 7? After 6, right? After 5, right? And again, because this is a 2-issue pipeline, so right now you can have 2 of them being issued at the same time, right? So how about 8? When is the earliest time I can execute 8? Question? Oh, 7 depends on, 7 depends on 6, right? So it's actually here. Okay, good catch. What else? So how about 5? How about 8? When's the earliest time I can put A? After 5, right? But when is the earliest issue slot for memory that is empty after 5? After 6? Actually, after 3, right? Because again, I still have only 1 memory unit and they have to be in order, right? So now if I have 9 and 10, when's the earliest time I can execute 9? Yeah, good catch. It's actually here. Okay. Okay, we should update this. Okay, let's make it. Let's just redraw it here on the fly. Don't make too many changes before the deadline of a paper. Okay, so here's the thing, right? You guys are right. The earliest place I can have 8 execution is actually, oh boy, then I have to change a lot. Okay, but it's not bad to walk through. Oh, okay, so 7 would go here, right? And how about 9? It's actually going to be a cycle earlier, right? Agree? Okay. And for 10, instruction 10, who is instruction 10? The move instruction is depending on 9, right? So where is instruction 10? Okay, so instruction 10 could be moved here. And instruction 11, where do I have 11? Okay, lovely 11 is here. 11 is here, and because I have 8, right? So 11 could be put here, right? Okay, so how about 12? 12 is depending on 5. So 12, we have no issue, right? No problem, right? And how about 13? It's right here, 13, 14, that's all okay, right? So now, how about 15. 14, 15. 15 is the move queue instruction depending on 12. So it's right here. And 16. 16 is the move queue instruction. So it's depending on, what is this? Oh, okay. 16 is depending on, okay, boy. Okay, 16 is depending on 12, and 17 is depending on 15. No, 17 is depending on 16, right? 17 is depending on 16. And 18 is depending on, no, sorry. 17 is depending on 16. So it's right here. 18 is depending on 15, right? And 19 here, 20 here, 21 here, right? So that should be the correct one, right? But again, right, if you check the execution, right, interestingly, you will figure out that, well, we are able to issue 14 instructions in A cycles. Every A cycles, I'm issuing 14 instructions, right? So my CPI would be very close to 0.5, but not 0.5, right? And one thing that is interesting is that if you check the figure, right? If you check this graph, right? Actually, sorry, here. When is the first instruction? 5, 10, 9, 8. Okay, where's 8? Okay, this is probably the right one. Okay, so if you check this graph, right? One thing you will figure out, right? For each iteration, my earliest instruction is always showing up here, and the last instruction in each iteration is also on this path, right? So this is actually the critical path of execution. What does that mean? If there's no way I can make this chain faster, there's no way I can improve the performance. Agree? If I try to optimize this part, does that improve the end-to-end latency? Not at all, right? So here you look, right? If you look carefully, right? For this side is what actually determines my performance. But for this part, right? Even if you try to improve that, for example, even if I can move 12 faster, even if I can move 19 faster, does that improve my performance at all? Not at all, right? So only this part is critical to my performance. So that's the critical path of execution. So if you want to count the CPI, one of the very first thing is that there are several ways you can count the CPI of your program. So for example, you pretty much find, okay, this part of graph is very repetitive, right? So you can count like, okay, how, on average, how many cycles it takes for this amount of instructions to execute, right? You find a repetitiveness, right? And the second thing that you can tell is that this is my critical path, right? So on this chain, who is the first instruction in my iteration? Enter this dependency chain, and who is my last instruction leaving this iteration chain, right? So for example, let's look at instruction 15 and 20, between 15 and 21, because that's more mature, right? So the earliest instruction entering the issue stage is actually here, right, 15. And the latest instruction within this 15 to 21 leaves this pipeline is actually 17 here, right? So 1, 2, 3, 4, 5, 6, right? So on average, each iteration, the earliest would be 6 by 6. However, it's more complicated here because there are some interleaving here. Like A starts here. However, the latest instruction actually ends here, right? So there are some interleaving here. So it's actually pretty hard to calculate that. So in this case, you probably need to look at 2 iterations. So that's why I'm saying like 14 instructions in 8 cycles, because for every 2 iterations, it will take 8 cycles for you, right? Through the data flow graph analysis. Okay, so now it's your turn. First of all, for this piece of the code, who is on the critical path? Following C statement of the code snippet. All right, let's see what you guys think. So, most of you think the answer is C. So, can I have someone explaining why do you think the answer would be C? Why do you think the answer will be C? Why is the answer C? How do you know? What? Say again.
You read current and then you write to it.
Okay, I read current and I write to it, but do I write to current? I reassign current every time, but why does that the critical path, or why does that determines the performance? There's data dependency, but why data dependency would? If I have data forwarding, why that would be an issue?
Oh, that's a pointer.
That's a pointer. So what's wrong with the pointer? It has memory access. How much time it takes for the memory? 4 cycles. How about others? Why others are not on a critical path? What? They are not memory, but they could be on a critical path either. B is what? Is what? B is not used in what?
It's not determining. Like,
It's not determining factor, but why?
because there's a condition like inside the while loop.
There's a condition inside a while loop. So
So that is only considering the current, not number of nodes.
okay, so those answers will not be accepted by the final. and you will not get credits. So because first of all, I don't think any of this would justify why it's not on a critical path. So how can I justify something is on a critical path? What are the methods that can show that? The data dependency graph, right? So you actually need to draw a data dependency graph. So first of all, the linked list code that I'm giving here is actually very easy to translate into assembly language. First of all, for the current equal to current next is actually a memory access, right? Because current next is just one element in a data structure. And every time, right, when I move this current, it's a pointer. So if you want to do pointer dereferencing, what you will have to do is that I access that element and put it into the destination register. And the next time you load from here, right? So that's why you see in the next cycle, I have the same thing, right? And you want to compare if it's null. So you have a test queue here, right? To test if it's 0. And if it's 0, if it's not 0, you continuously go into the loop. And add L1 to EAX, that's the node plus plus, right? So if you draw a data dependency graph like this, you will soon figure out, right? 2, 6, 10, the node plus plus, right? They are not on the critical path, right? For the branch 3 and 4, they are also not on the critical path. What's really on the critical path is 159, right? So you have to show me this to prove what you are saying is right. Question? So first of all, right, who is the earliest instruction in a loop who is the latest instruction in a loop that finishes execution? Who is the earliest to enter this loop? It's actually both on this side, right? And the other thing is that if you remove any of this, would that improve the end-to-end latency of an iteration? Not at all, right? So if you remove something that doesn't affect your performance, that's not a critical path, right? That's an algorithm definition. Okay, so now this is the data dependency graph I have for you, right? With that, can you tell me what's the average CPI of this pieces of code? All right, let's see what you guys think. Okay, we definitely need some discussion. So why don't you talk to your friends for another 90 seconds and let's see how do you sync up your answers. All right, after discussion, let's see what you guys think. It's more C and D, So what do you guys think? So this is a loop. Every iteration has 4 instructions. How do you count the CPI? And here's the data flow graph. How do you count the CPI? Total number of instructions? Okay, what's the total number of instructions we have? 16. Okay. Why do you think it's a 16? Because I have a 16 here. Okay, total number of cycles, how many? 16. 16 divided by 16, so that's 1, right? Okay, another way, right? What if I have an unlimited number of instruction iterations? What if I have 10,000 instructions? Are we going to draw the figure for 10,000 times? Okay, you find 1 iteration, right? So what's the latency for 1 iteration? Or where is the critical path? Which one is the critical path? 15913, right? So this is actually where I determine the performance. So what does critical path tells you? So first of all, right, there's always a 4th cycle that you must pay for each instruction on this critical path, right? If I have n iterations, how many of this will be on the critical path? N times 4 cycles delay that I have to pay, right? How many instructions do I have in the total program? N times 6? This is only 4, right? N times 4, right? So n times 4 instructions will take n times 4 cycles. So the answer is actually 4 divided by 4 equal to 1, right? So okay, you have a 2-issue pipeline, but if you have a linked list code, it's actually going to make your performance only half of the throughput that you have. And the critical path is on the instruction 1 and it maps to current equal to next because you have this pointer dereferencing, right? So let's see, how does that work on a real modern processor? So here's the code example that I have. So here is, I have 2 different pieces of a code. So I initialize the same amount of data, and I want to test how deep is my data structure. So the first one, I traverse it, use linked list. The first one is by the array, and the second one is by the linked list. And here, let me compare the performance among each of them. So both of them will give you the same answer, 4K. But if you check the performance, right, it's very different. Okay, let me run it one more time. Okay, if you check the performance, right, if you have a linked list, the CPI is actually more than 2, not just 1, right? But this is the processor that has the 4-cycle delay on the L1 access latency. Why my CPI becomes 2, not as 1 that as I analyzed? Because don't forget, if you are using a linked list, you also have cache misses, right? So 1 is the most optimistic estimation of the CPI. It will be even worse than that, right? And same thing for your array, you also have cache misses. So by default, if you have an array, that should be like 0.5, but it's actually more than that, right? So it's going to be slightly off, but even through this analysis, you will know most optimistic, the best the linked list can do is 1. And not only linked list has this structure, this problem, right? You can imagine if you are implementing a tree, and if your left child and right child are based on pointers, this is also the performance you are going to get, right? So in reality, when you talk about performance code, no one will actually implementing something called binary search tree. Very inefficient. Any tree structure that is node-based is very inefficient. So that's why in reality, when we talk about like data storage systems, we embrace the idea of B trees, because at least in each node, we can have hundreds of nodes inside. And at least within these hundreds of nodes, they are consecutive, right? So that's why B tree is more, B tree or B plus trees, they are more of a welcoming idea than a lot of like whatever tree you learn in the algorithm textbook, because they are very, very slow in reality. Okay, and this actually tells you about that, right? So whenever I have an assignment that tells you to optimize the performance, if you think about I want to build a tree on that, you are off, right? You are off, right? So to be honest, in reality, if I really care about performance, the best practice is that if you can avoid trees, don't use tree. If you can use arrays, use array. If you can hash, use a hash, right? Anything that's pointer related, they are terribly slow. All right, so you might feel that, okay, professor, you're talking something that's really complicated. Is that really something that I'm using every day? So now I'm telling you, this is the Intel processor that you are using throughout for your assignments, right? And if you look at their design, it's very similar to the graph that I show you, right? So now you understand a lot of stuff here, right? First of all, the BPU here is the branch prediction unit. And I have, based on the branch prediction unit, I would access my instruction cache. And those instructions will be decoded, right? So this is pretty much like instruction fetch. This is the decode. And here, there is a micro op cache. So in Intel architecture, although it's externally complex instruction set architecture, but internally, they will map each sys instruction into RISC-like micro ops. And once it's translated, it will be put into this micro op cache. And then when the instruction is when the instruction is translated into micro op, then in the meantime, when the time we want to execute an instruction, we will put this instruction into this micro op queue. So this is pretty much like an instruction queue. And then you will have renaming logic, right? You already see that allocation, renaming logic. And interestingly, they have this like move elimination. So in a hardware right now, they try to see, well, if there are two instructions that are moving data from each other, if that's the case, they will shortcut it. And then the scheduler is pretty much like the issue logic, which will pick an instruction into one of the issue ports. And the ports will be connected to either ALUs or AGUs. And the ALUs are the ones that perform arithmetic logic operations. And the AGUs, you can see 3 of them are connecting to the load units, 2 of them are connecting to the store units, which means that the AGU is used to generate address for memory instructions, and 3 of them could be used for loads, and 2 of them could be used for stores. So in theory, you can actually execute 5 ALU instructions in parallel, 7 memory instructions in the pipeline. So so with that, right, if you are always able to create a program that doesn't have any data dependency among instructions in each iteration, and each iteration you have 7 memory instructions that do not depend on each other, and you also have 5 ALU instructions that does not depend on each other, in theory, you can achieve a CPI that's 1/12, right? That's what the processor can do. And Intel processor nowadays also have the E-core, which is a less performing core. However, the big message here is that even with the less performing core, you still have a 5-issue pipeline that can execute 5 instructions together. AMD's Ryzen processor also have the same thing, right? It also have 4-issue integer pipeline plus 1 additional branch unit, and also 3-issue memory pipeline. So in reality, AMD processor can also have a minimum CPI equal to 1/8, right? So that's what the real processor is. So however, right, if you have you have this kind of processor, or say in general, if I have unlimited IOP, unlimited issue width, but if your code is pretty much like the linked list, right, doesn't help, right? So when you write your code, you must remember these are the characteristic of your processor, and you must write your code in a way in favor of the design. First of all, you have multi-issue pipelines, so you need to make your code available to exploit this parallelism. And the second thing, you have cache. So your code must have good locality to exploit cache. And finally, you have branch predictors. So you have to make your code more predictable for the branch predictor to take advantage from, right? So now, based on this, I'm asking your opinion about this program. So a programming challenge that I would typically like to give to students is that how can you count how many number of bits are ones within a number? And that's actually very important if you are doing cryptography, if you are doing communication, if you want to do sparse matrix multiplication, if you want to do fingerprinting, and if you want to do like a bit mask. Those are very important questions. So what exactly is pop count? So given that you have an input number like this, right, and its binary representation is this, and I count there are different, how many of them are ones, right? And turns out the output is 10, right? So that's the question about. So, well, I try to mimic LeetCode because I know a lot of you love spending your time on LeetCode, right? So now I have the driver program, right? And I want you to implement this pop count function, right? How are you going to do that? Mm-hmm. Okay, so that's actually, you can shift it, right? And then you do an end, right? So here I present 5 different implementations. Can you tell me which one would be the best on modern processors? All right, let's see what your initial thoughts is about. So, okay. All right, why don't you talk to your friends for 90 seconds? And let me see what do you guys think. All right, let's take a look what's after discussion. Okay, now more of you think it's D, okay? But, you know, seeing is believing, so let's run it, right? So maybe your discussion is wrong, or maybe some of you might have a different opinion, or maybe, you know, sometimes majority may not be the right. So let me run this demo real quick. So this is version A, this is version B, this is version C, this is version D, and this is the version E. All right, so let's run them and see what's going on there and take care. So every one of them, I have -03 enabled. So they are already optimized. So let's take a look how much time it takes for each to execute. So right now I'm executing A, as you can see on this cell, right? And it's been a while, and it's already past the lecture time. Okay, it takes 22 seconds for A to execute. Not too bad, right? But let's look at B. How much time it takes for B to execute? So let's keep waiting for a little bit. B is indeed faster, 12 seconds. And now let's look at C. So C only takes 5 seconds. Woohoo! Right? So let's take a look at D. D is even faster, 3.7. How about E? Right? How about E? How about E? Some of you say that, well, E is covered, so that's C. Right? How much time would E be taking? Right? So we can count, like, I think it's more than 10 seconds, right? Is it more than 20 seconds? It will be longer than A. Why do you think it's longer than A? Fringe prediction. Okay, leave the answer to the next lecture, right? But now you know E is very long, right? So a lot of people would like to use case, right? But this experiments actually tell you that's a terrible idea, right? So, okay, so the reason why I want to show you this demo before the lecture, because this weekend, hopefully you will be inspired by this demo to finish your programming assignment. All right, so E actually takes the longest, 54 seconds. All right, so before you leave the classroom, a few things that I want to let you know. First of all, well, the most important thing is because some of the time conflict. So from next Tuesday and the next Tuesday, my office hour will be pretty much 10:30 to 12, because if you can, because I found that the current office hour, no one actually comes. So maybe hopefully people would wake up earlier to come. And other than that, the rest of the stuff you can find online or from the slides. Other than that, enjoy the rest of your weekend. I will see you next week.